uses a different, he uses admittance, and admittance is 1 over the reactance, to me, it's okay, there's nothing wrong with it. But I like to express it my own way, if I may. So I want to express, in this case, the parallel circuit. So most of the time we're not worried about it. Mostly it's going to be RL parallel, RC in parallel, and RLC in parallel. So I'm going to take a look at all. Excuse me.
Bless you.
I want to look at all of these different circuits, and again, the way the book covers it, it uses admittance. The book covers using product over sum. I like that kind of. And my method is to stay away and keep it the simplest possible, using polar and rectangular format, and also looking at it the phasor diagram. To me, the phasor diagram is a key to solving many RLC problems. So I'll try to express it the simplest possible way to express, in this case, you solve parallel circuit. And then from there, obviously, you can look at the book and also look at the shelf and choose which way. But if I were you, I would choose this one, my way.
Your way on the highway.
Let's try looking at the RL parallel circuit.
Private diesel.
Now, to save time, I'm going to eliminate, doing the XOL calculation. I just sign it to say to me it saves time. So I'm just going to say XOL what XOL is. Let's say XOL is 8K. And let's say that R is 5K. 5K, 8K. And I'll say I have a, let's say, 80 volt RMS supply volt. I don't have to give you the frequency, you know why? Because there's only one frequency that the inductor would be 8K. So if I put something in there, it might not be right. Because I don't know, so I don't have to worry about the inductance and whatnot.
You already got the inductance.
I'm sorry?
You already got the inductance, XFL.
Yeah, but inductance is in Henry, millihenry, right?
Right,
This is inductive reactance.
right.
So the difference between inductive reactance versus inductance. Inductance is in Henry,
Right,
inductive reactance is in ohms.
okay.
So here is ohms. This is the resistance that inductor shows in AC current. So, but if I say 15 millihenry, that is fixed, doesn't change. However, this can change depending on the frequency. As you saw in the lab, as I increased the frequency, XLL increased. And I decreased the frequency, it decreased. There was a direct relationship between the two. So, in a sense, so I'm giving you is not inductance but inductive reactance. So I'm already giving the reactance. I'm giving you the resistance. I'm showing you all the opposition that they show to the current. That's not really the main subject here. The subject is to draw the phasor and determine total current, voltages, impedance, all your good stuff. Okay, so the way I would go about this is exactly opposite of the way the book and the way that the shelf shows you. I approach parallel circuit, I say, well, this is a kind of current-driven type of a circuit because, we have branches. Each branch is independent. The voltage is going to be the same across each one. So I can find the current right now. I don't have to find I total. I can find I1, and I can find, or should I say IR, and I can find I sub L. And then I'll worry about I total. Because remember, it was the other way around, series circuit. Series circuit, we find impedance, then we find V over Z to find I total. That's not the step. Here, I'm going the exact opposite day, which is find the current first, then find the impedance last. Okay, let's try it. Let's say that in this case here, I know I sub R is going to be V over R, which is 80 over 5K. How much is that?
$16 million.
16
Million.
amps.
Yeah.
Now I can also find I sub L. I sub L is V over X sub L. 80 again, over 8K. That's easy. That's 10 milliamp. Okay, now is the time for me to take a look at this and look at the phasor before I go any further. I like to draw the phasor on this one here. Now, if you remember, X sub L was going upward. When it comes to current, it's exactly opposite. So I sub L is actually going down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I sub 10 milliamp here. I sub R is 16 milliamp. R 1, 2, 3. I sub R. And now you see what's going on here. There's a phasors again. I sub R, angle of 0 degree. I sub L, angle of minus 90 degree. So when I'm looking at it, I'm finding now I total. So I total. And notice phase angle is also going to be negative. So now it's going to be a vector sum. So I can say I total is equal to square root of I sub R squared plus I sub L squared. And I see that I can tell in this case here that, so let's just go ahead and find this. So I get 16 squared plus 10 squared equals square root of it. How much is that? I'll put the numbers there.
18.9.
18.9
Yeah.
milli.
Milliamps.
Amps.
Yeah.
Kind of ugly number, but we'll go with that. 18.9 milliampere. So that is I total. I can also find here now, and looking at this here, I can say, oh, I can find theta here. Theta is going to be the arctangent. Obviously, it's going to be negative, because you see that negative, so it's a negative. Arctangent of X of L over, I'm sorry, I sub L. I sub L over I sub R. Opposite over the adjacent.
Is negative I sub L?
Now, you know what, if that case, then I would remove
Oh,
that.
okay, just going negative.
It doesn't matter how you put
Yeah.
it, as long as you end up with a negative number, yes, good point. I can say minus I sub L, or I can just say minus arctangent. This is probably better. So what's the angle here? Minus how many degree? what's 10/16 equals our tangent?
About 32 degrees.
How much?
32 would be negative 32 degrees.
Yeah.
Just a minute. I'll bring the cable.